Previous lecture was about context-free grammars representing context-free languages. So, after writing a grammar, we need to argue that its language is the required language. The agenda for this lecture is to discuss a proof technique which can be used to prove that what language is represented by a context-free grammar. So, the topic for today is proving correctness of context-free grammars. We can try to understand how the proof of correctness can be obtained by an illustrating example. Consider a context-free grammar G for the language A, which is a set of all strings over AB with equal number of A's and B's. The number of A's in the string must be same as the number of B's in the string. We have seen an example grammar for this language in the previous lecture, and this is that grammar with 4 productions. And the aim today is to prove that this language can be generated by this grammar, or this context-free grammar generates exactly this language. So, we want to prove that the language of this grammar is this set capital A, which is this language. So, how we can prove it? There are 2 sides of this proof. One is called the soundness of the grammar design. Soundness, which means if W is a string derived from the start symbol of the grammar, that means W can be derived from the start symbol using 0 or more steps, then we can prove that, or we have to prove that the number of A's in the string derived must be equal to the number of B's in the string derived. So, that is soundness. Soundness means whatever is generated is in the required language, is the soundness part of the proof. Now, the other part is called completeness, which tells any string in this language can be generated by this grammar, that is completeness. The language represented is complete in that sense. That is, if a string W is having equal number of A's and B, then W can be derived from the start symbol of the grammar using 0 or more steps. So, this is completeness. So, soundness says if something is derived, then that is in the required language. Completeness means all strings in the required language can be generated. So, both these are required for proving the correctness of the language represented. And we can prove both of these by using the principle of mathematical induction. And for any context-free grammar, the proving correctness largely depends on the statement that you are formulating, which is to be proved using principle of mathematical induction. we can see with respect to this example how the proof can be obtained, and for every grammar you need to come up with a claim like this. See, this is the set of all rules in the grammar given, and we are making a claim. What is the claim? If alpha is a sentential form, meaning any string of variables and terminals which is derived from the start symbol of G in n steps from the start symbol. See, we are going to apply principle of mathematical induction on the number of steps used to derive the string. Okay, so we are claiming that if alpha is a string of variables and terminals derived from the start symbol using n steps in the derivation, then alpha must contain equal number of A's and B's. Now suppose you prove this claim, then what you can conclude? Any string which is derived is a string of terminals, so definitely in this set. So this is actually a stronger statement than what we have to prove. We have to prove that a string of terminals derived containing equal number of A's and B's. But we are proving a more general statement which says that whatever string of variables and terminals you derive, that must contain equal number of A's and B's. So this is sufficient to prove that the the grammar design is sound. So the soundness. So we are going to apply the principle of mathematical induction to prove it. First is a base case, that is the number of steps is 0, meaning you are starting with S and you are not applying any step, means what you derived is the start symbol alone. So alpha must be the start symbol, because you are starting with the start symbol, you are not applying any step, so what you derived is the start symbol. In this case we are done because the number of A's in this string is 0, which is same as the number of B's, because it's just capital S, A's and B's are not there. So we have proved for the base case. Now you can go for the strong induction hypothesis, and we have to prove that when the value of n is k plus 1, this statement is true. So now we are going to derive the string alpha using k plus 1 step, using k plus 1 steps. And now if you look at these productions, you can easily observe that whatever you derive as a string of variables and terminals, if that string is containing a variable, it must be capital S, because that is the only variable. So this is a fair assumption. And beta and gamma are some arbitrary string of variables and terminals. S must be there, that is what I am taking. So I assume that in k steps I derived a string of this form, and this is a generic form because S must be there and before and after that something is there. You call that something beta and gamma. Then in one step you are deriving alpha, because we have to derive the string in k plus 1 step. So first in k steps you are deriving this, and then in one step you are deriving alpha is your assumption. Now first case, suppose here you can apply only one step. It can be one of the 4 productions. So there are 4 cases to be proved. The first case is when you apply the first production for this S. So what is alpha? Alpha is B, then S is replaced by ASB followed by gamma. So we applied the first production. Then what is the number of A's in this alpha, you just substitute alpha for as this value. So, this is this case. Okay, now how many number of A's are there? Now, if you look at in this string, there are a number of A's. With respect to that, you are replacing capital S with small a, capital S B. So, you are adding actually one A to this string. So, you can say that it is nothing but the number of A's in this string plus this A. That is what I am writing. Not difficult to see. Now, there is a trick. From the induction hypothesis, you can see that because this string is having only, this string is derived using only k steps. From the induction hypothesis, you can see that the number of A's in this string is same as the number of B's in this string. So, the number of A's same as the number of B's, that is the fact that I am using here. Because from the induction hypothesis, we assumed that if the number of steps in k, then the number of A's and B's are same. That fact is utilized. Okay. Now, what is this? You can easily say that if the number of B's in this string is this, when you replace capital S with small a, capital S, small b, you are adding one more B, right? You are getting one more B into this string. Okay. So, the number of B's in this string is nothing but the number of B's in this string plus this B. So, this is exactly what we have, and if you look at, we are proving that the number of A's in alpha is equal to the number of B's in alpha. So, we have done for the first case. Now, go for the second case. Suppose you apply the second production. This is the string that you are getting. You can verify it easily. Now, what is the number of A's in alpha? You substitute alpha here, and you can easily observe that it is the number of A's in this string plus 1, because here you are introducing only one A. And from the induction hypothesis, you can say that number of A's in this string and number of B's in this string are same. These two are same numbers. And now, if you look at this, and when you replace this capital S with the RHS of the second production, you are introducing only one B. So, you can easily say that in this string, the number of B's is nothing but the number of B's here plus 1. Very similar proof. So, we are proving that in the second case as well, the number of A's in alpha is equal to number of B's in alpha. Now, the third case where you are going to apply this production. So, here you will be replacing S with SS. So, what about the number of A's in alpha? You substitute alpha here, and when compared to this, you are replacing capital S with SS. So, you are not introducing any A's. So, it is same as the number of A's in this string. And from the induction hypothesis, we know that it is same as the number of B's here. So, you can say that okay, even if you replace S with capital SS, you are not introducing any B, so it is same. So, we are proving that the number of A's in alpha is equal to the number of B's in alpha in the third case as well. Now, the last case where you are replacing capital S with epsilon, so you are getting this, S is replaced with epsilon. And what about the number of A's in alpha, which is the number of A's in this string, which is same as the number of A's in this string, because even if you throw out S, you are not taking out any A's. So, same as this. And now, from the induction hypothesis, it is same as the number of B's here, and hence we are done. So, we proved that if a string of variables and terminals is derived from the start simple using n steps for any natural number, then that string must contain equal number of A's and B's. So, the soundness is proved because any string must be derived using a number of steps, and hence we are done for the soundness part. Now, it remains us to prove the completeness. That is, we have to prove that when a string is having equal number of A's and B's, it can be derived from the start simple of this grammar using 0 or more steps. And proving that is more tricky, and here for helping us in that proof we need a subclaim. And what is the subclaim? If W is a string of terminals with equal number of A's and B's, then we are claiming that W is of one of these forms. That is, W is a concatenation of X and Y such that both X and Y will have equal number of A's and B's. We will prove it. Or W starts with A and end with B, or starts with B and end with A. So we are claiming that these are the only three forms in which you can have a W with equal number of A's and B's. So which are the three forms? It's a concatenation of X and Y where both X and Y will contain equal number of A's and B's. Or it starts with A and end with B, or otherwise it starts with B and end with A. We can prove it by applying the method of, maybe we can first assume that W is not of the form 1. That means W is not of the form X followed by Y such that both X and Y contain equal number of A's and B's. We assume that W is not of that form, then we can prove that W must be of the second form or of the third form. If we are proving this lemma, the subclaim follows, because if W is not of the first form, it must be of the second form or third form is what we are claiming here. Proof. Suppose that W is of this form, that is, it is starting with A and ending with A. We have to prove that you cannot have this, because if W is not of the first form, it must start with A and end with B, or start with B and end with A. So we are assuming the opposite. W is not of the first form, but it is starting with A and ending with B. That is, the starting and ending with A's, not of the second or third form. Okay, then what can be W? W is something like starting with A and ending with A, and in between there is an arbitrary string Z. That is what we said. Now, if you look at this point, we know that in the whole W, number of A's and B's are same. So, just before the last simple, the number of A's in that string must be 1 more than the number of B's, because the number of B's in this string must be 1 more than the number of A's, because after processing one more A you will get equal number of A's and B's. So this equation must be true. I hope you are getting it, otherwise verify it offline, because after one more A, equal number of A's and B's, meaning now number of B's is 1 more than number of A's. Or you can write this equation as the number of B's is greater than the number of A's in this string except the last A. Okay, so at this point the number of B's is more. Now you look at an arbitrary point I during the processing. What can be the number of A's in this string? This dash represents this part of the string. So what can be the relationship between the number of B's in this string and number of A's in that string? We can argue that it must be greater than, because at this point it was greater than, and suppose at this point it is not greater than. Not greater than means in between at some point it went to 0. Okay, that is what I am saying here. Here it was greater than, the number of B's was greater than the number of A's, and suppose at this point you have less than or equal to means in between you got a situation where the number of A's and number of B's are same, then only you can get the opposite condition true. Okay, but that is a contradiction. If that is the case, that means at some point you can say that to the left the number of A's and B's are same, then to the right also the number of A's and B's must be same, because in the whole string the number of A's and B's are same. Then you can say that it is of the first form. So at a point the number of A's and B's are same means to the left and right the number of A's and B's must be same. So you call the left as X and the right as Y, then it must be of the first form. We already assumed that it is not of the first form. So this is true for all I. I can be any point from here to there. So we have this at this point as well, the number of A's is greater than the number of B's is greater than number of A's, which is a contradiction, because in this string you have 0 number of B's and 1 number of A's, and 0 is not greater than 1. So which is a contradiction. So we rule out this, and the contradiction is that we assume that it started with A and now ended with A, and for this equation to be true, this must be AB. Okay, so it cannot start with A and end with B. End with A. That is what we proved, and in a very similar way, we can prove that it cannot start with B and end with B. And hence we proved the lemma, and the subclaim follows, because if it is not of the first form, we proved that it must be of one of the other two forms. Okay, now try to remember the result. If the string W is having equal number of A's and B's, then it must be a concatenation of two strings with equal number of A's and B's, or it starts with A and with B, or in other words it starts with B and end with A. So these are the only three forms. Now we can prove the completeness. The completeness claim is this: if W is a sentence or a string of terminals with equal number of A's and B's, which is n for some natural number, then W can be derived from the start simple of the grammar. We have to use the principle of mathematical induction here, and that is why we assume that that number is n. We are going to apply induction on this n. So what is the claim? If W is a string of terminals with n number of A's and n number of B's for any natural number n, then W can be derived. Base case, the number of A's and B's is 0, meaning the string is null string. This is the only string where the number of A's is equal to 0, number of B's is equal to 0, and hence proved, because you can derive this string using up just one production or one step. So that is done. Now the induction hypothesis, which is the strong induction hypothesis, which assumes that if the number of A's and B's same is less than or equal to k for all values of k from all values of n from 0 to k, you can derive the string W if W is having k number of A's and B's. That is the induction hypothesis. When you just assume for one value k, that is the normal induction hypothesis. When you assume it for all values less than or equal to k, it is what is called the strong induction hypothesis, or that method is what is called the strong induction. Okay, now we have to prove it for the value of n k plus 1. That is the induction step. Now you consider case 1 where W is of the form xy. From the previous lemma or subclaim, we know that W can be of three forms: xy or a xb or b xa. Here is the first case when W is of the form xy. Then we can say that we can derive W like this. First you apply production number 3. What you will get? SS. Then from the first S, you can derive any string with equal number of A's and B's, because here the number of A's must be less than or equal to K, which is same as the number of B's. Because from the form we can see that neither X nor Y can be empty string, because you can easily verify that, then it cannot be of the first form. So both X and Y are non-empty, and hence from the induction hypothesis, because X is containing less than or equal to K A's, then X can be derived. So from the induction hypothesis you can derive any X with equal number of A's and B's, because the number of A's here is less than or equal to K. And now from this S you can derive Y using 0 or more steps, again from the induction hypothesis, because the number of A's and B's are same in Y and that number is less than or equal to K. From the strong induction hypothesis we know that Y can be derived. So for the first case we are done. Now for the second case, when W starts with A and end with B, we will be applying the first production as the first step. You will derive A as B. Now you have to derive Z from this capital S, which you can definitely derive as you know from the induction hypothesis, because see in this string you have K plus 1 A's same as the, which have to be same as the number of B's, and then S must contain number of A's 1 less than this string. So definitely the number of A's is less than or equal to K. So from the induction hypothesis any such string Z can be derived. So we are done in that case, and we have to prove the last case where W starts with B and ends with A. The proof is very similar. In the first step we will apply production number 2. Right now we have to derive Z from the from the variable S, which is always possible as you know from the induction hypothesis, because Z must contain less than or equal to K number of A's, which is same as the K number of B's. So we are done. Thus we proved the subclaim. We proved the claim because it follows from the subclaim. What is the subclaim? W must be of the form 1, 2 or 3, and in every case we proved that we can derive W, and hence we proved the completeness. Thus we proved the soundness and completeness of this grammar, and thus we can conclude that the language is the set of all strings with equal number of A's and B's. With this we are finishing this lecture, and I am giving you an exercise question for you to practice and understand. How can you establish that a grammar is generating the required language? Please try to come up with a soundness and completeness proof. Only when you do it for a grammar, for a new grammar, you can understand how exactly you can do it. Today we have seen how we can use principle of mathematical induction to prove the correctness of a context-free grammar. So there are two parts. One is soundness and the other one is completeness. Soundness means if a string is derived, that must be in the required language. Completeness means all strings in the required language can be derived. And we discussed it for context-free grammar, and the same technique works for all types of grammars, regular grammar and also other grammars that we will be learning in this course. Thank you.